miles, 740 kilometers. Father Town Airbus A319neo with 7% lower operating costs per seat. 93, 737 MAX 8. The Boeing 737 MAX 8 entered service with Malindo Air, wearing Batik Air Malaysia livery. The MAX 8, the first variant of the 737 MAX, has a longer fuselage than the MAX 7. On the 23rd of July, 2013, Boeing completed the firm configuration for the 737 MAX 8.94. Its first commercial flight was operated by Malindo Air on May 22, 2017. The MAX 8 replaced the 737-800 and competed with the A320neo. The 737 MAX 200, a high-density version of the 737 MAX 8, was launched in September 2014 and named for seating for up to 200 passengers in a single-class layout with slimline seats requiring an extra pair of exit doors. The MAX 200 would be 20% more cost-efficient per seat, including 5% lower operating costs than the MAX 8, and would be the most efficient narrow-body on the market when entering service. 95. In mid-November 2018, the first MAX 200 of the 135 ordered by Ryanair rolled out, in a 197-seat configuration. 96. It was first flown from Renton on the 13th of January, 2019, and was due to enter service in April 2019. 97, 98, 737 MAX 9. 737 MAX 9 first flight on April 13, 2017. The 737 MAX 9, the stretched variant of the MAX 8, was launched with an order of 201 aircraft in February 2012. It made its rollout on the 7th of March 2017, and first flight on the 13th of April 2017. Winking Sad Smiley 99, it was certified by February 2018. 100. The launch customer, Lion Air Group, took the first MAX 9 on the 21st of March 2018, before entering service with Thai Lion Air. 101. The 737 MAX 9 replaced the 737-900 and competes with the Airbus A321neo. 737 MAX 10. The MAX 10 was proposed as a stretched MAX 9 in mid-2016, enabling seating for 230 in a single class or 189 in two-class layout, compared to 193 in two-class seating for the A321neo. The modest 66-inch, 1.7 m, stretch of fuselage enables the MAX 10 to retain the existing wing and CFM LEAP 1B engine from the MAX 9 with a trailing link main landing gear as the only major change. 102. The MAX 10 was launched on the 19th of June, 2017, with 240 orders and commitments from more than 10 customers. 103. The variant configuration with a predicted 5% lower trip cost and seat cost compared to the A321neo was firmed up by February 2018, and by mid-2018, the critical design review was completed. 104, 105. The MAX 10 has a similar capacity to the A321XLR, but shorter range and much poorer field performance in smaller airports. 106. It was unveiled in Boeing's Renton factory on the 22nd of November, 2019, and scheduled for first flight in 2020. 107, 108. Boeing also considered parallel development with the 757 replacement, similar to the development of the 757 and 767 in the 1970s. 109. In the late 2010s, Boeing worked on a medium-range Boeing new midsize airplane, NMA, with two variants seating 225 or 275 passengers and targeting the same market segment as the 737 MAX 10 and the Airbus A321neo. 110, a future small airplane, FSA, was also touted during this period. 111. The NMA project was set aside in January 2020, as Boeing focused on returning the 737 MAX to service and announced that it would be taking a new approach to future projects. 112. Design. The 737 continued to evolve into many variants but still remains recognizable as the 737. These are divided into 4 generations but all are based on the same basic design. Airframe. The fuselage cross-section and nose are derived from that of the Boeing 707 and Boeing 727. Early 737 cockpits also inherited the eyebrow windows positioned above the main glare shield, which were a feature of the original 707 and 727. 113. To allow for better crew visibility. 114. Contrary to popular belief, these windows were not intended for celestial navigation. 115. Only the military T-43 had a sextant port for star navigation, which the civilian models lacked. 116. With modern avionics, the windows became redundant, and many pilots placed newspapers or other objects in them to block out sun glare. They were eliminated from the 737 cockpit design in 2004, although they are still installed on customer request. 117. The eyebrow windows were sometimes removed and plugged, usually during maintenance overhauls, and can be distinguished by the metal plug, which differs from the smooth metal in later aircraft that were not originally fitted with the windows. 117. The 737's main landing gear, under the wings at mid-cabin, rotates into wheel wells in the aircraft's belly. The legs are covered by partial doors, and brush-like seals aerodynamically smooth, or fair, the wheels in the wells. The sides of the tires are exposed to the air in flight. Hubcaps complete the aerodynamic profile of the wheels. It is forbidden to operate without the caps, because they are linked to the ground speed sensor that interfaces with the anti-skid brake system. The dark circles of the tires are clearly visible when a 737 takes off, or is at low altitude. 118. From July 2008, the steel landing gear brakes on new wings were replaced by Messier Bugatti carbon brakes, achieving weight savings to 550-700 pounds. 250-320 kilograms, depending on whether standard or high-capacity brakes were equipped. 119. On a 737-800, this gives a 0.5% improvement in fuel efficiency. 120. 737s are not equipped with fuel dump systems. The original design was too small to require this, and adding a fuel dump system to the later, larger variants would have incurred a large weight penalty. Boeing instead demonstrated an equivalent level of safety. Depending on the nature of the emergency, 737s either circle to burn off fuel or land overweight. If the latter is the case, the aircraft is inspected by maintenance personnel for damage and then returned to service if none is found. 121, 122. The original 737 with JT8D engines that span the entire wing chord. The original 737 with JT8D engines that span the entire wing chord. The 737 Classic with larger CFM56s. The 737 Classic with larger CFM56s. The 737ing with improved CFM56-7 engines. The 737ing with improved CFM56-7 engines. The 737 MAX has larger CFM LEAP engines with chevrons. The 737 MAX has larger CFM LEAP engines with chevrons. Engines. Engines on the 737 Classic Series, -300, -400, -500, and Next Generation Series, -600, -700, -800, -900, do not have circular inlets like most aircraft but rather a planform on the lower side, which has been dictated largely by the need to accommodate ever larger engine diameters. The 737 Classic Series featured CFM56 high bypass turbofan engines, which were 25% more efficient and also reduced noise significantly over JT8D low bypass engines used on the 737 original series, -100 and -200, but also posed an engineering challenge given the low ground clearance of the Boeing 737 family. Boeing and engine supplier CFM International, CFMI, solved the problem by placing the engine ahead of, rather than below, the wing, and by moving engine accessories to the sides, rather than the bottom, of the engine pod, giving the 737 Classic and later generations a distinctive non-circular air intake. 52. The improved, higher pressure ratio CFM56-7 turbofan engine on the 737 Next Generation is 7% more fuel efficient than the previous CFM56-3 on the 737 Classic with the same bypass ratio. The newest 737 variants, the 737 MAX series, feature LEAP 1B engines from CFMI with a 69 inches, 1.76 m, fan diameter. These engines were expected to be 10 to 12% more efficient than the CFM56-7B engines on the 737 Next Generation Series. 123. 737-200 JT8D engine with original cowling design. 737-400 CFM56 engine with an ovoid hamster pouch inlet with a flattened bottom. 737-800 CFM56 engine with a more rounded inlet versus the 400 due to a redesigned fin in the engine. 737 MAX 9 CFM LEAP 1 benzene with 787 derived engine chevrons flight systems. The 737 is unusual in that it still uses a hydromechanical flight control system, similar to the Boeing 707 and typical of the period, that transmits pilot command stow control surfaces via steel cables that run through the fuselage and wings, rather than by an electrical fly-by-wire system as used across the entire Airbus fleet and all subsequent Boeing models from the 777 onwards. 124. This has been raised as a safety issue because of the impracticality of adding redundant mechanical cable-based systems like the ones found in electronic systems. This leaves the flight controls as a single point of failure, vulnerable to wing or fuselage penetration by metal fragments from an uncontained engine failure, for example. 125. The primary flight controls have mechanical backups. In the event of total hydraulic system failure or double engine failure, they will automatically and seamlessly revert to control via servo tab. In this mode, termed manual reversion, the servo tabs aerodynamically control the elevators and ailerons. These servo tabs are in turn controlled by cables running to the control yoke. The pilot's muscle forces alone control the tabs. The 737 Next Generation series introduced a 6-screen LCD glass cockpit with modern avionics but designed to retain crew commonality with previous 737 generations. 126. The 737 MAX introduced a 415.1-inch landscape LCD screen cockpit manufactured by Rockwell Collins, derived from the Boeing 787 Dreamliner. Except for the spoilers, which are fly-by-wire controlled, and all the analog instruments, which became digital, everything else is similar to the cockpits of the previous 737 generations to maintain commonality. Original 737-200 cockpit, classic 737-300 cockpit, next generation 737-800 cockpit. Aerodynamics. The original -100 and -200 series were built without wingtip devices, but these were later introduced to improve fuel efficiency. The 737 has evolved 4 winglet types: the 737-200 mini-winglet, 737 classic forward/in blended winglet, 737 split scimitar winglet, and 737 MAX advanced technology winglet. 117. The 737-200 mini-winglets are part of the Quiet Wing Corp modification kit that received certification in 2005. 117. Blended winglets were standard on the 737 and are available for retrofit on 737 classic models. These winglets stand approximately 8 feet, 2.4 m, tall and are installed at the wing tips. They improve fuel efficiency by up to 5% through lift-induced drag reduction achieved by moderating wingtip vortices. 127. 128. Split scimitar winglets became available in 2014 for the 737-800, 737-900, BBJ2 and BBJ3, and in 2015 for the 737-700, 737-900 and BBJ1. 129. Split scimitar winglets were developed by Aviation Partners, the same Seattle-based corporation that developed the blended winglets. The split scimitar winglets produce up to a 5.5% fuel savings per aircraft compared to 3.3% savings for the blended winglets. Southwest Airlines flew their first flight of a 737-800 with split scimitar winglets on the 14th of April, 2014. 130. The next generation 737 MAX will feature an advanced technology at winglet that is produced by Boeing. The Boeing at winglet resembles a cross between the blended winglet and the split scimitar winglet. 131. An optional enhanced short runway package was developed for use on short runways. Blended winglet, standard wings, a retrofit option for classic split scimitar winglet standard and Layton's advanced technology winglet standard on MAX interior. The first generation original series 737 cabin was replaced for the second generation classic series with a design based on the Boeing 757 cabin. The classic cabin was then redesigned once more for the third, next generation 737 with a design based on the Boeing 777 cabin. Boeing later offered the redesigned Sky interior on the wing. The principal features of the Sky interior include sculpted sidewalls, redesigned window housings, increased headroom and LED mood lighting. 132, 133, larger pivot bins based on the 777 and 787 designs and generally more luggage space. 133, and claims to have improved cabin noise levels by 24 dB. 132. The first 737 equipped Boeing Sky Interior was delivered to Fleet Dubai in late 2010. 132. Continental Airlines, 134, 135, Alaska Airlines, 136, Malaysia Airlines, 137, and TUI Fly have also received